The last part of this chapter is going to be looking at conjugated carbonyls. We will often call them alpha-beta unsaturated ketones or aldehydes. Look down here at the structure, and you can see that the carbonyl is in conjugation with the double bond. And this is the alpha carbon, this is the beta carbon, and that's why they're called alpha-beta unsaturated. When we look at reactions that these undergo, we see that this entire bonding scheme here acts as one because it is one pi system. And just like dienes react as one pi system, so will conjugated carbonyls. Just like dienes will do either 1,2 or 1,4 addition, we also can have 1,2 or 1,4 addition to conjugated carbonyls. 1,2 addition means you have addition across this bond, and 1,4 means you have addition across the 4 and the 1. But we're going to see it doesn't really look like that's what happens because there's a rearrangement that occurs. But essentially, the first steps are 1,4 addition. When we were looking at dienes, it was the temperature that determined whether or not you had 1,2 or 1,4 addition. With conjugated carbonyls, it is the nucleophile that determines whether 1,4 or 1,2 addition occurs. When we have a soft nucleophile, which is not a strong base, it's a mild base, weakly basic, those things add 1,4. An example of that are amines and Gilman reagents. Strong bases add 1,2. Examples of that would be hydroxide or a Grignard reagent. Those are hard because we have a lot of concentration of charge in one place. When you have 1,4 addition, it actually adds here and here, but what ends up happening, a rearrangement occurs, so it looks like it really was 3,4 addition. 1,2 addition essentially is just addition across the carbonyl. So here's a 1,4 addition. Let's see what happens. An amine is a weak base, and so the nitrogen adds to this end of the double bond and then the proton up on the oxygen, and the double bond moves between, just like with 1,4 addition in the dienes. However, what happens with time, because this 1,4 addition gives an enol, enols usually rearrange to the keto or the aldehyde form, and so what happens with time is this then becomes a keto form. It's actually very quick. But what's the net addition? You can see the net addition is the nitrogen adds here, and the hydrogen comes off the nitrogen of the amine, and that other one adds there. So it looks like 3,4 addition. So here's an example of 1,4 addition, an amine adding to a conjugated carbonyl. Notice the nitrogen becomes attached here. So 1, 2, 3 from the end. 1, 2, 3 from the end. And then the hydrogen becomes attached where? Right there. And that's a CH2 you can see. So this hydrogen actually ends up on this carbon. It doesn't matter if it's primary or secondary. All amines, except for tertiary amines, they can't add they add reversibly because there's no proton to move to the number 3 position. Both primary and secondary amines give the exact same product. It's not like the enamines and imines, which it depends. Here you have the exact same product. Gilman reagents do 1,4 addition also because they don't have a lot of charge concentration on the carbon. And so where do they go? They go to the number 4 carbon. And then when you wash with acid, there's basically an enolate that's formed from the addition of the Gilman reagent to this carbon. You get a negative charge here in conjugation with the carbonyl, and then when you wash with acid, this carbon becomes protonated. But when you have a Grignard reagent, which has a huge negative charge on the carbon, what happens? You're not going to attack at the number 4 carbon, you're going to attack at the number 2 carbon. After it adds to the carbonyl, what happens is the proton on the oxygen down here comes from the acid wash. Okay, here is an example. We have lithium aluminum hydride. Remember that lithium aluminum hydride is very basic. So what is it going to do? 1,2 addition. This hydrogen ends up on the carbonyl here, and then the acid wash puts a proton on there. So you go ahead and try to figure out what is the outcome of these two reactions. Pause and then restart after you've figured it out. Okay, if I look at this, you can see the methyl group is in a Gilman reagent, so it's going to add 1,4. That's going to add to this carbon, and then the proton is going to end up being on this carbon here. So this is the product of this reaction. The Grignard reagent is very basic, so where does that end up? That ends up adding to this carbon, and we end up having the methyl group on the carbon, changing that to an alcohol. So how can you make 2-methyl cyclopentane carboxylic acid from 1-cyclopentene carbaldehyde? Pause the lecture and sit down and try to figure out what actually happens here, how you can do it. So how can you make 2-methyl cyclopentane carboxylic acid from 1-cyclopentene carbaldehyde? Well, the first thing you need to do is write the product that you want to get to. And let's just trace the carbons. This carbon must be this one must be this one, and this one must be this one. So automatically you must, hopefully, you're seeing this is conjugated and you've added a methyl group down here. So you think, well, the intermediate must be this one. And that makes a lot of sense because we know how to take an aldehyde to a carboxylic acid. So what are the reagents that we need to go from the conjugated aldehyde to the substituted aldehyde? Well, the Grignard reagent does that, not Grignard, excuse me. The Gilman reagent does that. Now you wouldn't want to use a Grignard because that would add to the carbon in the carbonyl. So we use the Gilman reagent, and then to take the aldehyde to the carboxylic acid, what would we do? We'd use chromic acid. So how can you make this compound from 2-cyclohexenone? Well, the first thing to do is to write 2-cyclohexenone down and try to figure out where in the structure those carbons are. And if you look, you can see an oxygen here and a 6-membered ring, and that just looks pretty much like it ought to be the 6-membered ring and this carbonyl being the source of the oxygen. And hopefully you're saying, this looks kind of like a Diels alder from this being added to this. If we do that, we can get this intermediate, and then that intermediate can be modified to this with a Grignard reagent. So now let's go ahead and see what we need in order to do these steps. In order to do the the Diels alder reaction, all we have to do is mix them together. So they form this. Then once we have this, what can we do to do this? Well, that's a Grignard reagent. So how can you make 1,4-dimethyl 3-amino-cyclohexanol from 4-methyl 2-cyclohexenone? Well, this is the 4-methyl 2-cyclohexenone. Let's go ahead and write down the product we want to get to. There is 1,4-dimethyl 3-amino-cyclohexanol. So how is it we can go through this process? Well, if I look at that, I think, nitrogen addition here Well, that probably is an amine addition to a conjugated carbonyl. And if I have that, well, then I can do a Grignard reagent to make that alcohol. So let's go ahead and put the reagents in. If I use ammonia, that's going to add across the double bond in that conjugated ketone. And then to get the alcohol from that carbonyl, we just use a Grignard again. Remember spectroscopy? We've really already learned all of these things. IR, we have a carbonyl, IR. Where do we see the carbonyl? 1685 to 1730 for aldehydes and ketones, approximately. You can get outside of that range occasionally. A hydrogen alpha to a carbonyl is going to be about 2 to 2.3. The hydrogen that is on the carbonyl of an aldehyde is about 10 in proton on NMR. If you look at the carbon in a carbonyl in C13 NMR, that's going to be around 200 parts per million. And don't forget that the aldehydes and ketones do alpha cleavage and McLafferty rearrangements.